Hello, and welcome to another of our video tutorials explaining the features of FORC 3. In this video, we'll be looking at how we can use FORC PCA to analyze a mixture of vortex states and multi-domain states, and split out those two components and analyze the proportions of each one. This tutorial accompanies the new paper explaining our updated FORC PCA method and is aimed at reproducing what you see in figure 5 of the paper. Okay, so we're going to begin with a fresh copy of FORC 3.05, and we'll start by using the Load FORC Files button to load in a set of FORC data that have been measured for a mixture of vortex states and multi-domain states. So here are our data, our raw FORC data. We'll select all of those and we'll load them in to FORC. Now you'll see as the data is loading that some corrections have already been applied to this data. The first thing we'll do, however, is we'll turn off all of those corrections and see how we can apply them one by one in the correct order. Here's all the data loaded in. First of all, I'm going to switch off all of these corrections initially. So we start with just the raw data as it's measured on the instrument and loaded fresh into FORC. So here are our data files containing the raw FORC curves. First thing we'll do is select all of the data that we want to analyze and process in the data browser. And now we can apply our corrections in order. The first one is to correct the drift for the instrument. The second one, which is optional of course, is to apply the first or last point artifact correction. And the next one is a new correction in this FORC PCA method, which is absolutely necessary in order to apply the new normalization procedure. So we're using a high field slope correction in order to normalize the data to an MS value of 1. And to do that, we specify a certain percentage of the data, and above that percentage we'll fit the data to get the high field slope. So with 85%, any data that lands between 85 and 100% of the largest field applied will be used to fit the data. Now, of course, we have to ensure that your FORC data is measured out to sufficiently high field to saturate the ferromagnetic component. So if we now click that button, it applies the slope correction so it fits the high field portion and then sets the MS value to 1. Now we can look then at all of that data and just check that it's worked as expected. So just a visual inspection to check that each data file is now been properly normalized to an MS value of 1. If not, we can adjust this number here. We can fit just an even higher field portion of the data, which is likely to undercorrect the data. Or we can include a much higher proportion of the data in order to do the high field slope fit, which is, you can see, is overcorrecting the data in this case. So I'm going to stick with the value of 85, which appears to give us good saturation behavior. Of course, as I said, it's up to you to ensure that your FORC measurement in the first place is measured to sufficiently high field for that correction to work. The next correction we do is subtract the lower branch in order to improve the processing of the data. So we now have our drift corrected, our first last point corrected, our normalized and lower branch subtracted data, and we're ready to smooth that data now for processing. So change the smoothing here. I'm going to use VaryFORC with parameters 7757.1, 0.1, and then in order to speed up the processing for this tutorial, I'm going to have a high output factor so that the processing happens extremely quickly. So here's our data processing. You might have noticed the second FORC in that data set was significantly noisier than the others, so we might want to go back to that data point and re-smooth it. So we can look at all of our data processed now. You'll see the second one here, WM2, is a little bit noisier than the others. So what I'm going to do is go back to just that data file here, and just apply a little bit of extra smoothing in the background just to lower that noise level down. Ideally, you would use the same smoothing factor for all your data points, but in this case, that one was significantly noisier. And so we've just increased the smoothing in the background a little bit there to bring that into line with the other data files. Okay, so that's our processed now and smoothed data. We can look at the range of data of interest. The vast majority is somewhere between minus 0.1 and 0.1, but we can adjust the region of interest that we're going to focus on when we do the PCA analysis. Okay, so now we're happy with the data, we can actually close all of that data now. So I'm just pressing the Option key down and clicking on the windows just to quickly delete those windows. Next, select the data we want to include in the PCA analysis. I'm going to include all of it. And now we're ready to start the PCA analysis. So bring up first the PCA analysis panel. And the first thing we need to do is to regrid that data. You'll notice that bringing up the panel brings up that results folder there. And we've still got all of the data that selected that we want to process. Click the PCA grid button. And this is where we enter our region of interest that we want to focus on with the PCA analysis. I'm going to leave this just at the default values for now. We can show how to change that later on. So we have a PCA range and a resolution of 1 millitesla. It now cycles through all of the data and regrids that data onto your, focusing on your specified region of interest and at the specified field resolution. Once that's done, you can click the Run PCA button, and that's done. The PCA analysis has been performed, and the first thing you will see is this scree plot, and this is a depiction of how much of the data variation is explained by the first, the second, the third, the fourth, the fifth, and the sixth, etc. principal components. And you'll see that, of course, most of the variation here is explained by the first principal component. In fact, if we bring up the info panel, drag the cursor onto here, we'll see that actually 99% of the variation in this data set is explained by just that first principal component. And that's because this is a binary system, just two n members, and that can be explained by a single principal component. The subsequent principal components are much smaller and are largely representing noise in the system. So most of the variation is explained by PC1, so we just need that single value. Well, we can either close this window now or minimize it. Okay. So the next thing is we choose which principal components we want to consider, and clearly in this case we just have a single principal component corresponding to the first eigenvector of the PCA analysis, so eigenvector 0, and we now can plot the results. So plot PCs, that brings up three windows. The first one you see here is a calculated fork diagram, then the calculated fork curves is the second one, and then the third window is the score plot. Just adjust the size of these. So on the right there you have your calculated fork diagram, in the middle the calculated fork curves, and over on the left is the score plot, in this case just with a single axis because we've chosen one principal component, and all of the data spread out along that single axis. Now there's a cursor added to that graph that we can either click and drag, or we can move with the arrow keys, and if you want to move faster with the arrow keys, just press the Shift button down and the arrow keys in order to move the cursor much more quickly. And you'll notice that as we move that cursor around the score plot left and right, the calculated fork diagram and the calculated fork curves change and update automatically. So at this point we're exploring the unmixing space and exploring what the resulting fork diagrams look like in different regions of the score plot. If I go over here to one extreme of the data, we can start to see a fork which looks like a multi-domain fork. we want to optimize the intensity range, we can use the auto scale intensity range feature. That's command 5 or control 5 on a PC. And that will optimize the intensity range for that chosen region. As we move the cursor around, the intensity range will automatically update to always reflect the range of intensities within the calculated fork diagram. But if you want to optimize that individually, you can use those menu options to do it. As I go over this side, we can see that we have a pseudo single domain or vortex state type fork diagram. But if we go too far beyond the data, we start to see that the calculated fork curves look odd. They're starting to be non-monotonic, so that tells us we've gone too far. And really, in this case, we go too far to the left. Again, we can see that the forks start to cross each other, and we get very large negative regions appearing in the calculated fork diagram. So really, things become unphysical the minute you go beyond the data in this particular case, and that's because our data set contains within it examples of 100% multi-domain and 100% vortex state samples. So we're happy that if we move the cursor to that data point, we can identify that as one of our key end members, our vortex state end member. So I'm going to bring up the define end members panel, click set EM1, and then I'm going to move over to the left here to the other extreme, and we can see now we're starting to see our ideal multi-domain. So I'm going to call that EM2. Calculate proportions, and now we can see the final result of the PCA analysis, which is our calculated proportions of the two end members and the fork diagrams that we've chosen for each to represent each of those two end members. So the proportions graph, you can see here, the red is representing EM1, the blue is representing EM2. And because this is a binary system, then EM1 is just 1 minus EM2 in this particular case. Now, if we want to compare those results with the known mixing proportions of this particular set of samples, I'm just going to load in from another experiment. I'm going to load in the known proportions, which is stored in a wave somewhere here called WM. I'm going to bring that in, dump it into the results folder. Now I can actually compare the calculated proportions, EM1 or EM2, versus the known proportions. So if I display EM1 versus WM, I get a graph here that plots one versus the other, and of course that should be a straight line with a slope of 1. Just going to draw manually a line here. With a slope of 1, although because my graph here actually isn't perfectly square, then that 45-degree angle is not quite 1-to-1, but I think I can fix that. Let's just make sure my graph is square. I'm going to make sure the graph is square, and then I'm going to redraw that line. Here we go. Redraw that line at 45 degrees. Okay, that represents our 1-to-1 line, and we can see now that we're doing a pretty good job. And if we compare that with what's in the paper, here's the figure from the PCA paper. We're essentially now reproducing that figure here. Okay. Now I said I would show you if we want to redo any part of the analysis. So I'm just going to show you now what to do in the case that you want to change anything. And the safest thing to do if you want to change anything is actually to start from scratch, delete all of the PCA windows, delete the results folder, select the data again, and re-grid. So by closing all the windows, deleting the results folder, reopening the PCA control panel, we can make changes to the way that we grid the data. Run the PCA again, and then plot the results. So all I've done here is regridded the data using a slightly expanded region of interest, and we get essentially the same results, but we're now seeing much more of the data that we want. And beyond that, the analysis runs in exactly the same way. But just to reiterate, if anything is behaving unusually, or you want to start again or change it, the way that we grid the data, the best thing to do is to close all of those windows, delete the results folder, close the PCA control panel, reopen it, and then start essentially the process from scratch. Okay, thank you very much. And we'll be producing additional tutorial videos that look through the other data in that paper.